little demo.
This is a demonstration of wave speed on a rope. The wave speed depends on the tension in the rope in an inverse relation, well, in a direct relationship, actually. So if we don't have much tension in the rope, the wave speed is fairly slow. But as we increase the tension in the rope, the speed increases, and then at higher tensions and yet higher tensions, the speed gets very high. So the little piece of tape in the middle of the rope actually helps you to visualize the amplitude of the motion as the rope comes up, comes back to its equilibrium position, and then down, and then back to its equilibrium position. This piece of tape indicates the amplitude, the distance from the equilibrium position, either to the positive point or to the negative point. The bottom line is that the wave speed is slow for low tension, high for high tension, and that's important for tuning your violin.
So the key here, if you want to write this down, is that we talked about this before, that the speed of a wave is dependent on the properties of the medium through which it's traveling. So in this case, it was a rope, and if the rope has a certain amount of mass, it has more inertia, then it has a certain speed. So you can imagine if you had a really light rope that has very little inertia, it's easy to get the particles to move, the wave speed will be fast. If you have a high inertia or a very heavy rope, the wave speed will be very slow because it's harder, it's more sluggish to get those particles to move, to get the energy to move through the particles. Remember, it's the energy that's passing through. The particles themselves don't go anywhere. They just go up and down, or if it's a longitudinal wave, they go side to side, but they don't go anywhere else. They don't move with the wave. And that's so important to remember. So it's the energy that's traveling at the particular speed. So it's only dependent on the properties of it. So further consolidation shows that, if you have a heavy medium, okay, so like a big, heavy slinky, or a big, heavy, sluggish, like let's say a big oil patch or something like a heavy material, waves will travel more slowly through that material. If you have a very light medium, like a really light slinky or a light rope, the waves will travel faster through that medium. Very important to understand that. Heavy medium, slower speed; lighter medium, faster speed. Tension is another property of the wave. So that tension, the higher the tension, the faster the speed. Imagine a guitar string. The tighter you tighten it, the higher the frequency, and you'll notice the waves will travel really fast up and down. Or if you make it really not tense, you lower the frequency, and if you flick it or you strum it, the wave will travel more slowly. So high tension, faster speed; low tension, low speed. Big thing here, amplitude. The size of the wave or the energy that you put into it does not affect the speed. It's only the material properties of the material or of the medium. And the last thing here is that, whether it's a transverse wave or a longitudinal wave, there's no real difference in the speeds of the waves. There's a slight difference for very complicated reasons, but it's more or less the same speed, whether it's transverse or longitudinal. So this summary here is super important. Please make sure you write it down, listen back to this, and make sure you understand it. It's going to become important for the next part. Okay. Waves at boundaries. Now, waves have this ability to transfer from one material or medium into another medium, okay? And the question becomes, what happens to the energy as the wave passes from one medium into another medium? What happens to the size of the wave, the speed of the wave, the direction of the wave, all that kind of stuff. So you can imagine, like, if you yell at a wall and someone's on the other side of the wall, well, the energy had to transfer through the air molecules, right? That energy had to hit the wall, and then had to transfer as a wave through the drywall, then through the air in between, or the insulation, and then through the drywall on the other side, and then back into the air to the person. So that wave went through multiple transfers from materials into other materials. Sometimes, even like, the mediums can be a lot different. So if you're in a cave and the material medium is rock, well, when you yell, you get an echo because the energy tries to transfer into the rock, but it can't really, so it reflects back. We call it an echo. So we're going to learn more about that as well. So we're going to talk about these boundaries, either really hard boundaries or really soft boundaries, or boundaries that are sort of in between. So like going from one slinky to a different type of slinky, or one type of water to a different type of water, or cold air to hot air, because the material is changing, so the speeds are changing and things happen. Okay, so here's a video that's going to show reflection. So we're going to look at when waves are incident, that means hit, a hard boundary, so meaning that the wave hits a fixed spot. And the second one is when it hits an open spot, so a non-fixed spot that can move. Okay, and so it's really important to look at how it reflects and how it works. We'll consolidate it later as well. So it's going to send a wave. It's going to send a crest on the one side, and you see it come back. Now look at when it hits a fixed boundary, notice what happens. It comes back on the other side. So you send in a crest, and it came back as a trough. It inverted. So the wave inverts when it hits a solid boundary, and that's a reflection. Now there's a loose end. This is an open end. There's no hard fixed boundary there. See what happened? It stayed on the same side. When it reflected back, boom, and it came back on the same side. See that? And then it does the inversion on his hand and then comes back on the same side. So watch, fixed end, inverts, comes back, same speed. Okay? In both cases. And there you go. Clearly an inversion. The loose end comes back on the same side. Look at that. And it inverts at his hand because that's a fixed spot. But notice his hand even moves a bit. It's impossible not to get your hand to move because it's a medium. So that's completely open-ended. And watch, it comes back on the same side, which is pretty weird. So that's reflection from a hard boundary and a very soft boundary. Again, we're going to consolidate that in a lesson after this, but it's really important to understand that. We're going to look at some images of that later as well. Okay, waves passing through boundaries. Okay, let's say that we have a really heavy slinky and a really light slinky, or a heavy rope and a light rope attached to each other. Okay, what we're going to do is we're going to send in a pulse. Okay, so we're going to send in a pulse, and so fast to slow, and this one here is slow to fast. So we're going to send in a heavy medium, large inertia, slow wave, and it's going to hit a fast medium here, which is a low inertia medium, and we're going to see what happens at the boundary.
Waves change when they hit a boundary between two different media. Part of the wave, called the transmitted wave, is transmitted across the boundary into the second medium. Part of the wave, called the reflected wave, is reflected at the boundary and moves in the direction opposite to that of the incident wave.
Notice how it comes back on the same side? So when it went slow, it bounced off the boundary. So some transmitted, some reflected. It's really weird. And the one that reflected came back on the same side because this is a less dense material. This is a more dense material, or a fast medium and a slow medium. And so the wave came back on the same side. The transmitted wave always goes through on the same side. If you looked at the energy that transmitted and the energy that reflected, they'd be the same. We'll come back to this. Now we're going to look at the opposite. Let's go from a fast medium to a slow medium. Can anybody predict what will happen? Think about it. You're still going to get a transmitted wave. You're still going to get a reflected wave. But what will it look like? What will the relative speeds look like? Fast medium, slow medium. Let's take a look. See if your prediction's right.
When a wave pulse traveling on a thin string meets a thick string, the thick string lifts slightly, generating a transmitted wave. Because the thick string has greater inertia, neither the speed nor the amplitude of the transmitted wave are as great as that of the initial wave. By Newton's third law, the thick string pulls back on the thin string with equal and opposite force. Because the thin string has a smaller mass density, it accelerates faster at the boundary, setting up an inverted, reflected wave. Note that the wave momentarily distorts as it rebounds off the boundary.
Was your prediction right? Did you predict that this would reflect back on the opposite side and that the wave would be smaller and moving at a slower speed here? If you did, good work. Okay, so some consolidation notes here, and then again, we're gonna have another video that will take it, finish it all off. Two things happen when waves reach a boundary. Part of the energy is transmitted into the medium. We call that the transmitted wave. And part of the energy moves backward from the boundary, what we call a reflected wave. Now, so there's always a transmitted, some of the energy transmits and some of the energy reflects. That always happens when a wave hits a boundary. Now, this sets us up to think about light. If you ever looked at a window, and you'll notice that you can see through the window, but you can also see the reflection. Well, it turns out that light behaves like a wave. And so you can clearly think, oh, light must be like a wave, because if it's both transmitting and reflecting, particles don't do that. Like if you throw a ball at a glass without it breaking, it doesn't partially transmit. Like part of the ball, it'd be weird, like a dimmer ball goes through one and then a part of the ball bounces back. So you have two balls at the end of it that are like, one went through and one came back. And not just weird, but a wave can do that. So light behaving like a wave will both transmit and reflect. And you did that in grade 10 science as well, where you did reflection and refraction. The refracted wave is the transmitted, and the reflected wave is the reflected wave. So take notes on that. Okay, so there's two cases. All right, when the medium changes, wave energy is both reflected and transmitted. We saw that. There's two cases. If the two materials that you have, right, if the difference is very, very different, like very, very small, meaning that if you have two ropes that are almost the exact same mass, but they're slightly different, almost all the energy transmits. Very little reflects back. If you have an instance where there's two media that are very different, so like a really, really heavy rope and a really, really, really thin rope, most of the energy just comes backwards. It just gets reflected back and none of it really transmits through. So write that down. And we're going to see a video, some things about that. Okay, is a reflected wave inverted or erect or upright? And so this is important to recognize. We've seen this already in that very first video about reflection. We saw that whenever a wave passes from a less dense, or what we call a fast medium, to a more dense, which is a slow medium, the wave is inverted. So watch, hits a heavy medium or a hard, like a fixed, and it comes back inverted. Watch this. Hits, inverts. Hits, inverts. So some of the energy comes back, some transmits, and see how it slows down in the slow medium. So less dense or fast medium to slow medium, it comes back inverted. The transmitted wave always goes through on the same side. Okay, well, what happens when the wave passes from a more dense, so slow medium, to a fast medium? Well, the reflected pulse is erect, not inverted. So watch this. Boom. Comes back on the same side. Back on the same side. What if it's infinitely different? Then all of it comes back. There's no transmission. This would be like if you have a loop there, and you saw that in that first video as well. Okay, we'll draw diagrams of these later as well when we consolidate it. All right, wave superposition, really important. When two or more waves interact with another, so this is another thing called wave interference. When two or more waves interact with each other, it's called interference. Okay, we're just going to watch a little video about this.
Good morning. All right, everybody, let's watch what happens when these two carts head straight toward one another.
Flippin' physics.
What just happened?
Yeah, that's not possible. I mean, the two carts cannot just pass through one another, right?
Right. As we all know, two objects cannot occupy the same space at the same time. So this is not possible. I used a green screen and two different videos to create the illusion of the two carts passing through one another. And this is what really happens. The two carts collide.
Cool. Cheater.
Wow. But my point here is that we are currently learning about waves, and we need to learn what happens after two waves are headed toward one another. So let's pause the demonstration and discuss it first. Class, are waves objects?
No.
No, waves are a disturbance of a medium.
Waves are energy traveling through a medium, so no, waves are not objects.
Correct. Waves are not objects. So waves behave differently than objects. In other words, because waves are not objects, they can occupy the same space at the same time. Which is why waves do not collide. Instead, when they occupy the same space, they interfere with one another via something called superposition. Let's watch what happens when the two waves interfere with one another. You can see that when the two wave pulses occupy the same space, the two wave pulses add together, and the resulting wave pulse is the addition of the original two. The general term for this interference of the two waves with one another is called superposition.
Superposition is the addition of waves when the waves interfere with one another. Got it.
The specific example shown here is called constructive interference because the two waves add up to a larger amplitude wave. And after the two wave pulses interfere with one another, the two waves continue on the spring with the same shape they had before. They continue on as if they had never occupied the same space and had never interfered with one another.
That makes sense because the wave pulse, which is stored energy in the medium, just continues on moving.
Wait a second. How do we know the waves do not bounce off of each other? It's not clear from the demonstration that they pass through each other and do not bounce off of each other instead.
Okay, Bobby, how about this as an example then? Does this help show that the two wave pulses do not bounce off of one another, but instead pass through one another?
Yeah, I can definitely see the wave pulses continue moving on after interfering via superposition. Thanks.
You are welcome, Bobby.
But this example cannot be constructive interference anymore, can it?
No, I bet this is called destructive interference.
Why?
In the previous constructive example, the two waves added to one another, constructing something bigger. In this example, the two waves seem to cancel one another out, and they no longer construct something bigger, but rather they seem to destroy each other. So I bet it's called destructive interference.
Bo, you are correct. This is called destructive interference. But I do want to address one word you used, and the word is seem. You said the two waves seem to cancel one another out. They do not just seem to cancel one another out. The two waves interfere via superposition, and actually, while they occupy the same space, do cancel one another out almost completely. And you can see that they do almost completely cancel one another out when we pause the demonstration at the moment when the two waves occupy the same space. You can see we very nearly have what is called total destructive interference. If the two waves have the same shape and amplitude, but are on opposite sides of equilibrium, then we do get total destructive interference. The reality is that it is difficult to show a real example of total destructive interference because the two waves need to be perfect inverses of one another.
It's okay, Mr. P. I can see exactly what you were talking about. If it was total destructive interference, the spring would be completely straight while the two waves totally destructively interfere with one another, right?
Thanks, Billy, and yes, you are correct. So there you have it. Because waves are not objects, they do not run into one another. Instead, waves interfere with one another via superposition, and more specifically, they can constructively and destructively interfere with one another.
When two or more waves interact with one another, it is called interference. Remember, they don't bounce off each other. They pass through each other, right? Particles don't do that. Waves do that. There are two types of interference, just so you can write this down. The first one is constructive interference. When the wave displacements are in the same direction, the resulting wave has a larger amplitude than either of the original waves. Destructive interference, if the wave displacements are in the opposite directions, the result is a wave with a smaller amplitude than the individual waves. So, the principle of superposition we're going to see in a second just says, if you've got two waves, let's say they both have an amplitude of 2 in the same direction. When they interact, they have an amplitude of 4, then they pass through and they go back to 2s. If you have one that's a positive 2 and a negative 2 and they come near each other, you'll get completely destructive interference during the time they meet. But when they pass through, the 2 amplitude and the -2 amplitude will just continue. If they're not the same, let's say it's 1 and 2, positive both, you get 3. If you have a crest of 1 and a trough of 2, so that's a 1 and a -2, you end up with a -1 when they interact. So you get a small bump below, right? And that's the principle of superposition. That's how all waves interact. In fact, if you look at water waves in the ocean, it is a superposition of thousands of waves, right? So all the little ripples and all the things you're seeing, all the big waves and whatever you see, that is actually the result of the superposition of hundreds or thousands of different waves interacting with each other instantaneously at all points in time. And so you get these weird undulations happening all over the place. And it's very neat to sort of break down. If you think about when people talk to you and all the different frequencies of sound that you hear, when that comes to you, it comes to you as one wave. And you have to deconstruct all the individual waves that were there and sort of deconstruct the wave that was superimposed in the first place. All right, writing down the principle of superposition is, it's the displacement of a medium caused by 2 or more waves is the algebraic sum of the displacements caused by the waves. So all that means is that, again, here you're going to get constructive interference. If this is amplitude 4 and this is amplitude 2, then 4 and 2, and then it becomes 2 plus 4 is 6. So your wave that you see is 6. You don't see the 2 individual waves, and then when they pass through, the 4 continues through, and the 2 passes through on the other side. And the 2 waves completely pass through one another. They don't bounce off of each other. It's so important. See the directionality of the arrows. But while they meet, the principle of superposition says just take the 2, or if there's 5, 6, 7, 1,000 waves, it doesn't matter, right? Fourier analysis, there's some really cool math that comes out of that. Doesn't matter how many waves there are, you just add them up, positive or negative, in terms of whether they're crests or troughs. It's very, very simple to do. All right, this guy's pretty funny. So there's a quick little, I think it's a multiple choice problem. So you can actually try it on your own while they're doing it and see if you can get the right answers. And they explain it really nicely. And nope.
Good morning. While I do prefer to show real demonstrations of physics concepts like we did last time, like this, wave interference via superposition is a topic where we should go over some idealized multiple choice problems. So here goes.
Flippin' physics.
Bo, please read, and Bobby, please answer the first problem.
2 wave pulses on the same string are headed towards one another as shown. When both occupy the same space, which diagram best describes the resulting waveform? Wave pulses are shown with different colors to make them easier to visualize and talk about. Does that mean the top illustration is all one rope, even though it is black, red, and blue?
Yeah, if I made the whole illustration black, it would be more difficult to discuss and visualize what happens. Bobby?
Okay, well, this is just interference via superposition like we did last time and you just demonstrated. So we draw both the red and blue waves in the middle at the same position and add their amplitudes together. The correct answer then has to be number 1.
I think it is also important to remember that after the 2 wave pulses interfere with one another, they continue on with the same amplitude and direction as before, right?
Bobby and Billy, you are both correct. Bobby, could you please read, and Billy, could you please answer the second problem?
Two waves on the same string are headed towards one another as shown. When the red wave occupies locations C and D, and the blue wave occupies locations D and E, which diagram best describes the resulting waveform? Wave pulses are shown with different colors to make them easier to visualize and talk about. Again.
Okay, well, let's move the two waves to their respective locations and see what happens. In locations C and E, the waves do not overlap, so they do not interfere at all with one another. So the answer could be 1, 2, or 4. In location D, the two waves are mirror images of one another, so the two waves end up completely canceling one another out in location D.
That is total destructive interference.
Right, so the correct answer is 2.
Correct.
But what happens when the two waves occupy the same space?
Then the waves actually end up having the same exact shape in the same location, and we get constructive interference. That means the resultant wave has twice the original amplitude as the two original waves.
And after the two waves interfere with one another, they continue on with the same amplitude and direction as before.
Very nice, y'all. Okay, let's do one more problem. Billy, please read, and Bo, please answer the third problem.
Two wave pulses on the same string are headed towards one another as shown. When both occupy the same space, which diagram best describes the resulting waveform? And then there's the same statement about the wave pulse colors.
Okay, so let's start by moving the two wave pulses to the middle where they overlap and occupy the same space. Well, that's not as easy as it was for the first two examples.
You could start by looking at specific locations.
Like the edges of the wave pulses.
Sure, let's start with the left edge of the two pulses where the...
Call it location A. It's always better to give things names.
Fine, look, location A, the left edge of the two pulses where the red pulse is at its maximum amplitude and the blue pulse is 0. When we add those together, we get the maximum amplitude of the red pulse. We can also look at the right edge of the two pulses. Let's call it location B.
Thanks.
At location B, the red pulse is 0 and the blue pulse is at its maximum amplitude below equilibrium. So the result is the maximum amplitude of the blue wave below equilibrium. That means the answer has to be either 3 or 4 because only 3 and 4 match what we figured out about locations A and B.
You're doing a great job, Bo. Please keep going.
Okay, well, let's pick another location. How about right in the middle? We'll call it location C. At that point, the amplitudes of the red and blue pulses are the same magnitude, with the red above equilibrium and blue below equilibrium. Then the two waves cancel one another out right in the middle. That means we know the answer, well, it's still 3 or 4 because both of those have 0 amplitude in the middle. So we need to pick another location. Let's say 1/4 of the way to the right of the left edge. We'll call it location D. At that point, the red wave is 3/4 of the maximum amplitude and above equilibrium, and the blue wave is 1/4 of the maximum amplitude and below equilibrium. Those two waves add up to half the maximum amplitude above equilibrium. Therefore, the correct answer must be 4, because 4 is at half the maximum amplitude above equilibrium, 1/4 of the way to the right from the left edge, location D. Choice 3 is less than half the maximum amplitude at that point. So yeah, it has to be choice 4.
And after the two waves interfere with one another, they continue on with the same amplitude and direction as before.
Really?
Again?
Yes.
Very nice, everybody. Okay, so please, when you see questions like these,
So it's a little more advanced than you fully needed, but I think I wanted to give you that opportunity to see. They're not hard to do, and if you have grid paper, you can set it all up. You're just adding or subtracting and looking at what's happening, and for those types of problems for superposition. All right, this video is a summary. It's going to summarize everything that you've just learned. It's going to talk about reflection, reflection, transmission, all that kind of stuff. So just watch this, and that'll conclude the lesson. And then there'll be a consolidation, very short consolidation lesson that comes after this in a different video that will, we'll draw some of these things in and talk through it. And that way, by you writing it and drawing it, it's going to really help you.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 109. It's on wave interference. In other words, what happens to waves when they hit objects or hit other waves? All the animals pictured here use echolocation. What does that mean? They generate sound waves that reflect off objects, and when they come back, they can figure out what they're looking at. Now, waves will also hit other waves, and as they do, sometimes the overall wave becomes larger, and sometimes it becomes smaller. So let me give you an example of that. I've got a slinky here, and I'm going to send two waves towards each other. Watch what happens when they meet. So the wave becomes bigger. But did the waves bounce off each other, or did they move through one another? Well, it's kind of hard to tell. Since both waves are on the same side, we don't know if they bounced back or if they went through. So a better way to figure this out is to send waves on either side. So I'm going to send a wave from the left on the top and from the right on the bottom. You can see they interact, but now the wave on the bottom continues to the left. And so when waves hit, they interact, but they move through each other. They're not reflected off of each other. And so wave interactions can take place when a wave interacts with an object, hits an object, or hits another wave. So when that interaction is with another object, we get reflection. It bounces back. Now, it depends on what we're hitting as to how we bounce back. And so if it's a fixed object, the wave, for example, the slinky hits something that doesn't move, it'll actually be inverted when it comes back. In other words, the wave goes in this direction, it's on the top, and when it comes back, it's going to be on the bottom. That's only if it's a fixed object. What happens if it's a free object? Well, the opposite happens. And so as it comes in now, let's say that this is able to move back and forth. The wave comes in on the top and it goes back on the top. And so that's reflection. Now when waves hit each other, we get what's called interference. Two waves interacting. That interference can either be constructive. Constructive is when two waves comes towards each other and they're both on the top. So what do we get? When they hit, we get one big wave. We're adding those waves together. So we're constructing a bigger wave. If it's destructive, we're on either side, and what do we get? We cancel each other out. So we are destroying the size of that wave. And so we use the law of superposition to figure out how big that wave is. And it's really easy. If you're 1 centimeter on top on both of those waves and it's constructive, we just add 1 plus 1 and we get 2. And so as waves bounce back and forth, what we can do is we can build up what are called standing waves. Waves that appear to not move, but what they really are is the addition of the waves bouncing back and forth. And so let's look at this using a PHET simulation. Let's start with a fixed end. So remember, if it goes into a fixed end, watch what happens. As it comes back, it's inverted. So it went down on the top and it came back on the bottom. Watch what happens if we now change that from a wave interaction where we have a free end. So it has the ability to move up and down. It comes back on the same side. And so again, it depends on what we're hitting as to how we come back, but we are coming back. We are being reflected. Now let's move into interactions between waves, when waves hit waves. And so that can be, remember, constructive or it can be destructive. And so let's start a wave moving down. So let me pause it for a second. Do you remember what's going to happen? We're hitting a free end. And so what's going to happen to that wave when it comes back? You should have said it's on the same side. And so let's do that. We were right. But you can see that I also generated a wave that's now moving from the left. These are about to hit each other. And so what's going to happen as they interact? Well, we should see constructive interference. And let's watch what happens. So we get one big wave right when they come together. Now what's going to happen to the wave on the left? Well, it's hitting a fixed object, so it should be inverted, and the one on the right should hit an object that's free, and so it shouldn't be inverted. So now what's going to happen when they hit? Should have figured this out. This is destructive interference now. And so watch what happens when they hit. They should cancel each other out. And we can just see this reflection and interference and reflection again. Example of this, I'm going to take a slinky and really send a pretty big wave. We'll do this in slow motion. You can see I kind of almost knocked my camera over. So the wave is moving to the left. It hits a fixed object and it was inverted. It hit my hand, which is a fixed object, and then it's going back in the other direction. So that's going to be that reflection of the wave. Now what will happen is if those waves keep bouncing back and forth and back and forth and back and forth, they're adding to and subtracting from each other, and so you get what are called these standing waves. And this is a sim bucket simulation. So you can see the green wave just appears to stand there. It's not moving. But what's really happening is that we have waves moving back and forth. So we have a blue wave that's moving to the right. It's reflecting back, and then it's moving to the left as this orange wave. And so as they move, they are interfering with each other. And so let's just grab one section right here. So why is this low? It's because they each are moving down from equilibrium, and so we just add those two values up. Why is the green right here at the middle? It's because...
Okay, so I'm going to pause it there. That's a little bit of an introduction to something we're going to learn about later called standing waves. And so I'll revisit this at that point. But up to now, you can see that was a pretty good summary of what you've just learned. And we'll do the consolidation lesson next.